Hello again. In previous segments, we introduced you to the basic tools and techniques used in fault analysis. And now, let's tie all this information together by looking at some real-life case histories. We've already examined a case where a line tripped out of service and reclosed successfully. Now let's consider case 1, an unsuccessful line reclosure. In practice, this happens quite frequently when the line does not stay de-energized long enough for a temporary fault to clear on its own. In this example, the oscillograph has captured the substation bus voltages in all three phases, the transformer neutral current and line current for one of the transmission lines. The oscillograph system in use here can record 3 cycles of pre-fault data. From the trace of line current, you can see that the line we have monitored is not the faulted line. This is obvious since the current resumes its normal load level after the fault is cleared. From the bus voltages, we conclude that the fault is a single line-to-ground fault on A phase. This is confirmed by the transformer neutral current. We can also tell that the fault duration is 4 cycles. And the line dead time is 11 cycles. At this point, the breakers on the faulted line reclosed, but the fault was still there. So the breakers immediately tripped out again and locked out. If this problem repeats itself over a period of time, we may conclude that 11 cycles of dead time is not enough to allow the temporary fault to deionize and dissipate. In this case, the dead time would be increased by changing the time delay at the breaker. Our next case history, case 2, shows what happens when the nature of the fault itself changes during the disturbance. Here we have a fairly extensive 69 kV subtransmission system that experiences a fault on the tie line between substations Y and Z. The 69 kV system is delta connected, but effectively grounded through zigzag grounding transformers located at substation X. Notice that all the oscillograph equipment is installed in substation X, remote from the fault location. In spite of this distance, we can still obtain a great deal of information from the recordings. The oscillograph has recorded 69 kV bus voltages in all 3 phases. Neutral current in a grounding transformer, and current in the bus tie breaker, all 3 phases as well as the residual current. The total elapsed time between the initial fault and final breaker clearing was 65 cycles, just over 1 second. Notice that we have broken the traces to indicate where the waveforms just repeat themselves. After 3 cycles of pre-fault recording, we see the onset of a single line-to-ground fault. This fault was actually caused by a tree falling across one of the phase conductors. The tree provides a path to ground. Looking at the oscillogram, the transformer neutral current and the tie breaker residual current both clearly show that the fault is line to ground. The high C-phase current in the tie breaker and the low C-phase bus voltage tell us which phase has been faulted. The single line-to-ground fault endures for 25 cycles. At this point, the C-phase conductor burns open, allowing the tree to fall onto A phase. However, the tree still maintains contact with C phase. Now, the nature of the fault has changed to a double line-to-ground fault. Over the next 5 cycles, you can see the effect of the 2-phase fault. Both A phase and C phase currents in the tie breaker rise sharply. Both A phase and C phase bus voltages are depressed. Transformer neutral current and tie breaker residual current are both still present, but they are reduced in magnitude. This is because a double line-to-ground fault is more balanced than a single line-to-ground fault. At this point, breaker Y finally trips to clear one end of the faulted line. the tripping occurs 30 cycles after the initial line-to-ground fault started. This is reasonable since we are dealing with a high-impedance fault. Thus, the level of fault current is low, resulting in a relatively long operating time. For the next 25 cycles, we still have a double line-to-ground fault, but the current magnitudes are very much reduced because one end of the line is open. You can see that the A and C phase bus voltages are back to near normal. At this point, the fault again changes. The A phase conductor now burns open. The tree contacts B phase and falls to the ground. But all three open conductors are now in contact with ground, resulting in a three-phase to ground fault. For the next 10 cycles, we have a balanced three-phase fault. You can see this from the three fault currents in the tiebreaker and the fact that neutral and residual currents are now zero. Breaker Z at the other end of the faulted line now trips to completely clear the fault. This occurs 35 cycles after breaker Y trips. Again, this is reasonable because the fault current is low and also because the fault is in zone 2 of breaker Z's protection. Thus, tripping is further delayed. This example has demonstrated two things. First, the nature of a fault can change during a disturbance, and in this case, the protection operated correctly to clear the fault. Secondly, our example showed that recording equipment located several buses away from the actual fault can still provide valuable information during a fault investigation. Let's now move on to our third case, an overtrip for a remote fault. This is a clear example of misoperation. Breaker A at 115 kV substation Z trips for a remote fault on the 230 kV system. With the help of the oscillographs located in substation X, we were able to spot the problem and correct it. In substation X, the oscillograms monitor the transformer breaker's A phase current and the zero sequence residual current. Also monitored are the 115 kV bus voltages in all three phases, as well as A phase and residual current for breaker B connecting to substation Z. You can see the onset of a single line-to-ground fault on the 230 kV line. The fault was on A phase, as shown by the sharp increase in A phase current through the transformer breaker and breaker B, and also by the depressed A phase bus voltage. The presence of zero sequence in the breakers also indicates a ground fault. Tripping on the 230 kV system was correct, and the fault was cleared in just over 3 cycles. But look at the phase current through breaker B. Normal load current flows after the 230 kV fault clears, but 5 cycles later, breaker A trips at the remote end of the line. The incoming feed from substation Z is now interrupted. After 14 cycles, breaker A recloses and remains closed. Further investigation revealed that while the fault was on, breaker A received the proper carrier blocking signal. But this signal was removed too quickly. As a result, the relays at breaker A saw fault current as well as a green light to trip. The problem was solved by resetting the timing of the carrier block signals. Again, this is a case where the overtrip problem may have gone unnoticed if we had not checked the oscillograms. Okay, let's take a break now, and then we'll come back and describe some more examples. In the meantime, switch off the videotape and review your written materials.